Hi everyone, this is Mr. Youngren again, and we are in our final two lessons of your entire Algebra 2 experience. And they're actually both just solving equations. Well, we're going to start off by solving exponential equations, and we've actually kind of already done this, but not quite to the extent that we're going to cover here in this lesson. So this is page 206. I know it's kind of cut off there, but this is where you're going to pick up. And as always, I have an opening problem for you, which you should be able to solve this point. So you're actually able to solve an exponential equation without me actually showing you. How you're going to want to do this is think about what would the corresponding log equation be that would allow you to solve this equation. So go ahead and hit pause. I want you to work through this on your own. And then when you're ready to check to see how you did, go ahead and hit unpause and see if your work matches up with mine. All right, so if we would have gotten the corresponding log equation, we're not ending with necessarily a number. Unless you've got a calculator, then we can end with the number. But essentially, with the skills we have up to this point, I can go ahead and say, if I have 2 to the power of x plus 3 equals 16, I'm going to convert that to a log, where the base of my log is still going to be 2. And just like you've seen me do in plenty of videos, I'm going to switch the position of the other two terms. So now instead of 2 to the power of x plus 3, it's 2 to the power of 16 equals x plus 3. And so in order to get x by itself, I need to subtract 3. So this right here is really an answer. It's just not a number yet. Now, based on which calculator you have, you might be able to plug this in and come up with an exact value. If you have an older version, you're going to need another skill or another rule in order to type it in your calculator that we're going to actually cover in this lesson. So for those of you that have a Texas Instrument, one that's you're able to choose the own base, we can actually come up with this value pretty quickly. And so how I'm going to do that is if you hit this math button, this is where a lot of the hidden functions are. And so if I hit math and I start scrolling down, I'm going to eventually run into this thing that says log base. And like we would expect, that's going to allow us to choose any base. So I'm going to put 2, and we're taking log base 2 of 16, and it can just come out as a whole number, which is 4, which means I have 4. And if I subtract 3, I get 1. So I get x equals 1. Now, could I have gotten there a little bit quicker or another way? Absolutely, right? I could have also said, hey, isn't 2 to the power of 4 16? Yes. And so in order for me to get 2 to the power of x plus 3 to equal 16, I would need to set these two things equal to each other, x plus 3 equal to 4. And after I subtract 3, I can get x equals 1. So lots of different approaches of how I can get to this answer. This is kind of more formal. This was maybe a way that you could have done up to this point. But either way, we're getting to that same answer. Now we're going to just equip you with even more tools and how we can solve these. So let's go through a few examples. So the first example is if we recognize on both sides, if we're trying to solve an equation, that they can be written as a common base, that actually makes it really simple for us. And that's what we're going to want to do here. So what this first step is saying is rewrite the equation such that b to the power of n equals b to the power of m. What that means is we want to have base that is the exact same. In this case, I have a base of 2. And so I'm wondering, can I rewrite 16 as a base of 2? And the answer is yes, right? In fact, I already have that in my calculator. 2 to the power of 4 is 16. So what I'm going to do is instead of 16, I'm going to write this equation as 2 to the power of 3x minus 8 equals 2 to the power of 4. So this is what this is saying. I now have a common base. This exponent would be the n. This exponent would be the m. So the next thing is set the exponents equal to each other. Now, why would I do that? When you think about what it means to be equal, we want everything to be the same. So if the base is already the same, we now just need the exponents to be the same. So we're going to set those equal to each other. 3x minus 8 equals 4. And that's really easy to solve, right? That's just a linear equation now. And so I can add 8 to get 12, divide by 3, and I get x equals 4. Pretty simple. Now, if you're not confident about this answer, check it. If you plug this in, 3 times 4 is 12, minus 8 is 4, 2 to the power of 4, we've now seen for the third time, is 16. So that does work out. So really, in these first few problems, we're trying to find a common base. Once we have that common base, let's just set all the equations equal to each other. So what I'm going to do is, why don't I go through 1 and 3, allowing you to do the even problems, either on your own or with your teacher. So 27 and 9, I actually could write, well, be careful here. I'm kind of tempting to want to say 9 squared is 27, but that's definitely not the case. So I'm like, I don't really know what that base might be, but maybe I can write 27 as a base of 3. Is 3 cubed 27? Yes, it is. So I'm going to rewrite 27 as 3 cubed, which is still to the power of x plus 3. And 9, I know I can write as 3 squared, and that's to the power of x minus 1. So I'm like, what the heck do I do? Well, a couple lessons ago, we talked about our exponent rules, that if we have an exponent raised to another exponent, I need to multiply. So I'm having to multiply 3 times x plus 3, which means I need to distribute the 3 to the x and the 3. So this is really 3 times 3x plus 9 after multiplying. And this is really 3 times 2x minus 2. Now we have that common base, and I can take those exponents and set them equal to each other. And then once again, once we're here, the solving is pretty easy. So I can add 2. So I have 3x plus 11 equals 2x. I can minus 3x, so I have 11 equals negative x, and divide by negative 1, and x equals negative 11. Now again, if I get here, I'm like, it seemed to make sense, but I don't know for sure. I'm just going to plug it in. So I'm going to see if I put negative 11 in here. Negative 11 plus 3 is negative 8. So what's 27 to the power of negative 8? And then some weird number. Do I get that same weird number when I plug in negative 8, or excuse me, negative 11 for the other equation? Well, negative 11 minus 1 is negative 12. And 9 to the power of negative 12. Oops. Let's fix that. Is that the same weird number? It sure is. 3.540700616 e negative 12. I'm not going to get into what that means. If you're curious, ask your math teacher. But that seems to work out because I get the same thing on both sides when I plug it back in. All right, so let's actually call that one good, as that's going to be the most complicating one that we might see where it's not real obvious. In 2, I don't need to rewrite 5, but you're going to want to rewrite 125. In 3, you're going to need to rewrite both 8 and 4 as a common base, 2. And then 4, the bases are already the same. So those will be pretty straightforward. So that's one tool that we can add in to our toolbox of how we can solve. Now, if we get to another problem where maybe we can't find a common base, and this is probably more common, at least in the real world where exponential equations show up, where I might not be able to get something or both sides as a base 2 or a base 3 or something along those lines. So how can we do this? We're going to do it very similar to how we found inverses, where we're going to get the exponential term by itself and convert it to its corresponding log. So the first step here is telling us to isolate the exponential expression. For us, that's 4 to the power of x minus 2, which means I need a minus 3. So after I'm minus 3, I get 4 to the power of x minus 2 equals 15. Now, I can clearly see this now. There's no way that I can rewrite 4 and 15 with a common base. So that's kind of why we need another tool. So the next thing is take the proper inverse log to undo the exponential. This is where we're having to convert this exponential into a log statement. So I'm going to write the word log. The base of my exponential is the base of my log. And I want to change the position of the other two things. So instead of 4 to the power of x minus 2, I want it to be 4 to the power of 15 equals x minus 2. And so now, to get x by itself, I just need to add 2 to both sides. So log base 4 of 15 plus 2 equals x. Notice how I did put that 15 in parentheses, because otherwise it might seem like I want to add 15 plus 2 and take log base 4 of 17, but that's not what we want at all. Okay, this is log base 4 of 15, and whatever that number is, we're going to add 2 onto that. Now again, if you don't have a calculator, this answer is acceptable. This is exact, but we want to find ways to actually come up with that. So you're going to have to get your hands on a calculator, ideally a graphing calculator. If you have a scientific calculator, you're going to be able to work with these as well. So one that looks like this, you should be able to work with that. Actually, I'm not seeing a log button on here. There's a natural, oh yeah, there is. There is. So you can do it with either one. And it's going to be the same of how we're going to do it either way. That scientific calculator won't have the log base button like what I'm going to show us right now. So again, for those of you that have this newer calculator, I can go ahead and hit math. I can figure out what log and choose my base of 4 is. 4 of 15. and then I can add 2 to that. And so really, our solution is x equals 3. Let's round to 3 decimal places, 953. And there's a solution. So if you're like, I got every part except for this plugging this in the calculator, and you have an older calculator, just hang with me. I'm going to show you a way of how we can actually come up with this or using any calculator, period. We're going to do that here at the bottom of the page. But what I want us to do is let's work through one more together. Okay, let's do number 5, where again, we're going to work on first getting the exponential term by itself, which is 7 to the power of x plus 4. So to do that, I'm going to add 19. So that gives me 5, 7 to the power of x plus 4. 23 plus 19 is 42. Right, 33, 42. Let's just be confident. I don't want to mess up on the video. Yes, it is. And then I need to divide by 5. That's what's going to get that final exponential term by itself. Now, I don't need the parentheses around the 7. If you want to keep them there, fine. It actually does not make a difference. 42 divided by 5, does it work out to be a nice decimal? Yes, it does. And what I mean by nice decimal is it doesn't repeat. It ends, right? It's just 8.4. And so now I can go ahead and write my corresponding log. So log base 7 of 8.4 equals x plus 4. So all I need to do is subtract 4 from both sides. And I have x by itself. And I'm done. So again, we want to come up with a value here. Let's actually skip to the bottom and come back to this and show us how we can do this with any calculator. And for now, again, if you don't have a calculator, this is acceptable. This answer will 100% work. So here at the bottom of the page, it says sometimes we might want to estimate the actual value of our solutions. I've kind of already showed you a way to do that. Without the use of a fancy calculator, excuse me, we'll have to use what's called the change of base formula to give us a decimal answer for this type of problem. The change of base formula allows us to take any log and then convert it into a log base 10. Every calculator, not every, but most have just this log button. That log button does not allow you to have any base. That base is just 10. So whether you're using a graphing calculator, new or old, or even a scientific calculator, there's a log button, both of which are log base 10. So if we use this change of base formula, I can use that log base 10 to come up with an approximate answer. And so what we end up doing is we take the log of whatever we're taking the log of, so log of m up top, divided by the log of the base. And remember, these are base 10. It also would work with natural log. It really doesn't matter. We can choose any base with this change of base formula. So how does this work out? Well, if I have log base 7 of 13, and I want to use the change of base formula, I want to convert it to a log with a base 10. So up top, it's log base 10 of 13, so what I was taking the log of, divided by the log of the base, which is 7. And I can type this in with any calculator. In fact, I'll show you how I do it on the more basic calculators. So log of 13, notice how there's not a base there. It actually is log base 10 divided by log of 7. And that'll give me an approximate answer of, again, let's round to 3 decimal places, 1.318. And we have an approximate answer. Let's just go ahead and do one more. So if I'm trying to find this base, why don't I use natural log this time? It doesn't matter. We can use any of them. All calculators, so scientific has a natural log button, that ln. The graphing calculators also have an ln button, new and old. So I'm able to take natural log when I'm taking the log of, which is 22, divided by the natural log of the base, which is 13. And so I can do that in my calculator. Natural log of 22 divided by the natural log of 13, and it gives me 1.205. Now, just to show you, if I would have done the same thing with a log base 10, I'm going to get the exact same thing. So log 22 divided by the log of 13. No difference at all. So it doesn't matter which base we choose, but the whole point of that is we're now able to use the base that is on your calculator if you don't have that fancy log base button. So now let's come right back up top and let's look at how we can maybe come up with an approximate answer here. Well, if I don't have that log base button, I'm going to have to use the change of base formula for this log base 7 of 8.4. And I'm going to go ahead and use log base 10. So this is now log base 10 of 8.4 divided by the log of 7. and then I'm going to minus 4 from whatever that is. So now, using any calculator, in fact, I actually think your phone calculator, which isn't very good, can do this as well, is 8.4 divided by log of 7 gets me to 1.094. If I want to keep this exact, so I could write this down with 3 decimal places, but I like to keep it as exact as possible. So actually what I'm going to do is I'm going to hit the minus button without doing anything else. Your calculator says ANS, meaning it's keeping the previous answer. And I can subtract 4, and there's our answer. The x is negative 2.906. And that's it. So you have one left to do. Number 6, you also have a change of base formula down here. Actually, why don't I just show us this one, because this is an exception here, because we can't take the log of negative numbers. So even if I try the change of base formula of log of negative 3 divided by log of 6, whatever calculator you're using, it's going to yell at you and say, I can't do that because you can't take the log of a negative number. I'll be like, oh yeah, I forgot. So log of 6. Non-real answer, just like I said, we can't do that. So we would say NA. Okay, we're going to end right there. You are now equipped to solve any exponential equation that you run into. Have a great rest of your day, and make sure you complete your video checking.